It should be visible. So thanks
Yes.
everyone for joining. Thanks first of all to Professor Naoui, to Sharaf and Ale, everyone in the organization committee. The support has been amazing. And thanks for involving me. It's really my pleasure. Thanks everyone for joining on a Saturday morning for this talk. As the professor said, I'm Leonardo Micheli from Sapienza University of Rome, and I am gonna talk today about the impact of dust storms on the large scale capacities of photovoltaics, a work I conducted with colleagues from my previous university, University of Caen, recently. So the reason for this job starts from one fact, from the from what we are living every day. So the fact that actually photovoltaics is delivering daily, every day, more and more energy to our electricity grid. So photovoltaics is actually giving us more and more of our electricity demand. So in this plot, I just shared some of the market share of photovoltaics in the electricity mix of three important European countries from a photovoltaic perspective, such as Italy, Spain, and Germany, where you can see that right now photovoltaics is representing already more than 10% of the electricity demand. Now, with great power comes great responsibilities. And what this means is that when photovoltaics start delivering so much electricity that is needed for our needs, any disruption in its performance can have some severe repercussions. And these are not just local repercussions, but can be also regional or national consequences. And in particular, one of the events that can actually impact photovoltaics at such large scale are dust storms. So probably most of the attendees knows these events much better than me, but let me quickly recap what this phenomenon consists of. We are talking about the large suspension concentration of dust and sand particles in the atmosphere. These dust clouds can travel for thousands of kilometers, and the most evident effect of dust storms is a clear reduction in the intensity of the irradiance that is then needed by photovoltaic panels to generate electricity. Here you can see how the visibility change during dust storms, and these phenomena are a growing concern worldwide for several reasons, starting from some social and health-related issues. Indeed, also the Food and Agriculture Organization of the United Nations raised concern related with sand and dust storms. And what I found more interesting about their statement is that the impact that these events have on solar energy is one of the actual consequences highlighted also by this statement, stressing out how dust storms do not have just a social and health impact, but have also consequences on our photovoltaic panels. So the relation between dust storms and photovoltaics is quite clear, is quite intrinsic. Indeed, we know that the locations that are more prone to solar energy, those that have the higher potential for solar energy in terms of resources, such as a clear sky, direct irradiation, and that have the lower cloud cover, are also those that typically are more exposed to dust storm and to the concentration of dust, which in this case is expressed through the dust optical depth. as attenuation in light due to suspended dust. So the locations that have the higher potential, that are more interesting for photovoltaics, are also those more exposed to dust storms, because either they are themselves arid and desertic locations, or they are quite close to them. However, this is not just a problem of proximity, because dust storms and dust intrusions can travel for thousands of kilometers, as you can see in this slide, where you can see the main sources of dust storms. Clearly, the Sahara is one of the major source of dust worldwide, followed by deserts in China and Central Asia and Saudi Arabia and Australia. But as you can see, there are clear paths that the dust can travel, and therefore these events can actually reach locations that are even far away from their source. Just to give you some examples, Saharan dust storms have been reported, for example, in multiple occasions on the UK. This was a first warning raised in 2023. Here you have a second event of orange sky reported for London, as you can see in this image. However, we have report of dust storms also, for example, for Eastern Europe and Russia. And in 2020, a dust storm was so big that also got his own name, Godzilla, and traveled up to the east coast of the US, creating also some health concerns over there. So essentially, no location is safe. We have similar um, examples, for example, for Japan, where there's a dust storm from China arrived, and for other locations worldwide. Now, as solar energy researchers, as solar energy experts, we are interested in dust storms because they can have two type of effects on our photovoltaic panels. The first one is what we call a concurrent effect. So is an effect that takes place at the same time as the dust storm and consists in a reduction in the intensity. So the suspended dust clearly scatters, reflects, and absorbs part of the incoming sunlight. And therefore, the photovoltaic panels see less irradiance just because of the suspended dust and suspended sand. However, after the sky has cleared, the effect of the dust storm can persist. And for these reasons, we also talk about a subsequent effect, which consists on the increased accumulation of particles, a phenomenon known as soiling, on the photovoltaic panels, which therefore continues to reduce the irradiance reaching the semiconductive materials, again, even after the sky is cleared, even after the dust storm has passed. And just after this talk, we're going to have a workshop specifically looking at soiling. So stay tuned if you are interested in the topic. So what me and my colleagues at the University in Caen were mostly interested in was really to understand the magnitude that of the impact that these events could have. And to do that, we really looked at the impact that a dust storm could have on the national grid. So on the whole electrical system of a big country. To do that, we looked in particular at the case of Spain, that was subject to a dust storm in March 2022, which was particularly intense. Here you see an actual image from Malaga in Andalusia, southern Spain, over that period. So the event that we will be discussing about took place in the second half of March, and was essentially really divided into two events. A first event, extremely intense, going from March 13 to March 19, and then a second event, much less intense, but slightly more prolonged, that lasted until the end of the month. In both these cases, we had Saharan dust being transported over Spain, and then even traveling through the rest of Europe. So as I said, what we wanted to understand with this work were both the the magnitude of the dust storm itself, as well as its electrical impact, its consequences on the photovoltaic production. So to do that, we looked at a number of variables at a number of parameters. Some of them are going to be listed here, and we're going to start with data regarding irradiance and their quality data, which we downloaded for the whole peninsular Spain. In particular, we looked at irradiance data downloaded from the Copernicus atmospheric monitoring services. And in this case, we looked at both actual weather data, so realistic conditions experienced on different sites across Spain, as well as cloud-free data. So the irradiance values that we would have had if there were no clouds in the sky. We also look at parameters that would give us information about the concentration of particles and dust in the atmosphere, namely PM10, PM2.5, and aerosol optical depth, which is a parameter that again describes the attenuation of light caused by aerosols suspended in the atmosphere. In addition to that, since we were specifically interested in dust terms, we also looked at a different parameter, which is known as dust optical depth, DOD. This in particular described only the impact of dust on the attenuation caused by the AOD, eliminating the impact of the other aerosols. We also downloaded again from Copernicus data related to cloud cover and rainfall. So all this data helped us to quantify the extent of the dust storm itself, but we also wanted to look at its impact on the photovoltaic performance. And to do that, we downloaded from the electrical grid operator website data about the photovoltaic capacity in Spain, which at the time was in the range of 19 gigawatt, the daily PV generation data, again at peninsular level, and the daily electricity demand. And we use those data to calculate for each day a market share, so the amount of electricity demand covered by photovoltaics, as well as a capacity factor, a parameter that is telling us how close is a system working to its ideal performances. And as you can see, is calculated as ratio between the actual electricity generation divided by the nominal capacity multiplied by 24 hours. Essentially is a parameter that is telling us how close an energy technology is working to its nominal capacity for across the day. So let's start and dive a bit into the results. And over here on the left, you see the daily clear sky global horizontal irradiance. Again, global horizontal irradiance that would have been registered on average over Spain if no clouds were present. What we did was actually comparing the actual data that you see represented in blue with the forecast produced using a univariate forecasting tool known as Prof based on previous year's data, as well as an uncertainty interval for our forecast. Also in red, you see the period in which we were interested or that we are actually investigating. So as you can see, the clear sky global horizontal irradiance has quite a smooth trend, but there is a clear drop, immediate, quite a severe drop at the start of the dust storm. And in particular, on March 16th, few days after the dust storm started, we registered a drop in clear sky irradiance as high as 23%, meaning that about a quarter of the irradiance was blocked by the suspended dust. After that day, the irradiance quickly recovers, but then, as you can see, we have a new period in which actually the performance are lowering again, even if by a significantly smaller amount. So overall, what we found was that over the 2 weeks period during which the dust storm took place, we had about a loss in clear sky GHI of 7% on average. Again, the worst drop was on March 16, and the distribution in the drop of clear sky global horizontal irradiance can be seen in this image, where you can see darker colors, darker red to black colors in those areas where the drop was much higher. And as you can see in some areas of Spain on 16th of March of 2022, we had a drop in clear sky irradiance as high or higher than 40%. This is particularly intense in the central part of the Iberian Peninsula, which is also an area that is hosting a substantial capacity of photovoltaic that will therefore have a significant effect on the electrical, on the performance drop that we are going to see later on. These results are actually confirmed by looking, for example, at the aerosol optical depth and at the dust optical depth. So just to give you an idea, typically we consider a cloudy day, if the AOD value is above, or not a cloudy, actually an hazy day, if the AOD value is above 0.4. Here, as you can see on March 16th, we have values that went actually as high as 2 or higher than 2.5 in some occasions, highlighting an extreme hazy conditions. Again, we see that most of the losses are in the center, in this case, slightly southern west of the Iberian Peninsula. And overall, what we found was that the dust itself was responsible for 40+% of the drop of the attenuation in irradiance caused by the aerosols. So on average, we also saw a significant increase in haziness in the atmosphere, again confirming the significant impact of the dust storm and the geographical scale of this event. This clearly had also an impact on the electrical performance. Again, we are talking about a solar capacity that at the time was 19 gigawatts. And what we saw was again shown in this slide, where you can see the actual data in blue, a black dotted line showing you the expected forecast, and then some forecast uncertainty. As you can see, during the dust storm period, there is a very clear drop in capacity factor for the Spanish photovoltaic capacity, with a drop that is much higher than the actual uncertainty intervals, especially during the first period that, as we said, was characterized by quite an intense dust concentrations. In particular, what you can see is that photovoltaics was expected to work at a capacity factor close to 20%, but in reality, it was working at capacity factor of 10 or even less than that. So by doing the analysis, what we found was that photovoltaics, and again, we're talking about 19 gigawatts of photovoltaics on average over a 2 weeks period, worked at half of the capacity factor that they were expected to work at. What this means is that 19 gigawatts of photovoltaics actually delivered half of the energy that they were supposed to deliver over a 2 weeks period. On the worst day, again, March 16, the drop was as high as 80%, meaning that photovoltaics delivered only 20% of the energy that it was supposed to deliver on that day. Clearly, this also halved and reduced the market share of our technology, meaning that the grid also saw only half of the expected energy coming from photovoltaics. On the worst day, only saw 20% of the expected energy coming from photovoltaics, and highlighting the need to take into account how such events can actually impact the photovoltaic performances, and therefore highlighting the importance to identify solutions to increase the resilience of the grid, even in high PV penetration scenarios. As I said, this was just during the dust storm. What I did with our colleagues was also looking actually at the subsequent soiling losses. And actually, what we found, interestingly, is that after these dust storms, soiling losses across Spain were quite limited. Actually, we're not really far away from the losses that are typically experienced in that period. Actually, this, while interesting results, should not be taken as a conclusive remark, because we know from previous work, such as those published by Conceição in 2018, that similar events actually can cause severe drops in performance, here represented by a drop in soiling ratio. Here, indeed, you can see how dust storm that took place in February 2017 caused a soiling loss of about 7 to 8% in Portugal, followed by another event in March that caused a loss of 3 to 4%. So even if in this case, despite the magnitude of the dust storm, soiling was not present, we should not take for granted the assumption that soiling will not happen in these conditions. However, you might have noticed by looking at the daily capacity factor distribution that actually this was not the only period in which photovoltaics was performing outside of the uncertainty range. Indeed, as you can see, there are multiple days in which the performance of the national capacity factor drops below our forecast uncertainty, highlighting a severe underperformance. Well, for Spain, just in 2022, we found about 20 days of severe underperformance, during which the capacity factor dropped by almost 60%. Again, highlighting that photovoltaics can significantly and surprisingly underperform on selected days. This did not just happen in 2022. By repeating the analysis on multiple years, you can see how many red bars we have, each highlighting a day in which the photovoltaic capacity was below or far below the expected performances. In particular, this is the case of Spain. If we take the 10 worst days since 2015, we have an average drop in capacity factor of 40%, which means that for about 1 month per year, for about 30 days per year, the photovoltaics is working at about close to half of its performances. In about 1% of its days, as you can see, the drop is as strong as 80%. Okay, and this corresponds to about 3 days every year. This is not just valid for Spain. The same analysis is being repeated also, for example, for Germany and Italy, as you can see in these two slides. Again, color coding is the same, where you see each red bars were severe underperformance, of course. Even in this case, you can see if we take the 10% worst days, we can have average drops in capacity factor ranging from 37 to 50%. And the more we lower the bar, if we go to 1%, to the worst 1% of the days, you can see that we have so clear drop in capacity factor that, again, we should take with care as solar energy researcher in order to make sure that, again, we are not putting at risk the reliability and the resilience of the electricity grid. So as we've seen, there are several days of underperformance. I'm talking today about dust storms. I don't want to give the message that these are all due to dust storms. Indeed, what the main cause of this underperformance are probably the presence of clouds. And this is kind of illustrated if we look at this graph, where you can see 3 different European countries, and you can see the cloud cover data. So the fraction of the sky covered by clouds, with lower value meaning a clear sky, higher value close to 1, meaning that the whole sky is overcast. As I said, we have the average cloud cover, total cloud cover, over days in which the performance were within our uncertainty values, and total cloud cover over those days where a severe underperformance was measured. As you can see, moving from normal days to underperformance day, the total cloud cover in both Spain and Italy, for example, raised from about 0.4 to about 0.7, 0.8. Something similar happens to Germany, where even in normal day, we might have an average total cloud cover of 0.7, so quite a cloudy sky. But even in this case, underperformance tends to occur when the sky is even cloudier. So when we have 0.8 to 0.9 total cloud cover values. However, cloud cover is just one of the parameters that we can use to predict and estimate such days. Because, for example, other parameters we can use to understand whether underperformance might be occurring are, for example, again, the aerosol optical depth, AOD, in this case measured at 550 nanometers, as well as the dust optical depth, again measured at 550 nanometers, which are again a good proxy to understand whether also a dust storm or some kind of dust related event is occurring. As you can see, even in this case, we find a clear increase in both AOD and DOD in some cases when severe underperformance is registered, meaning that, again, also the aerosols and dust storms might be contributing substantially to the days of underperformances. You can see in Spain, we go from median, I mean, for all countries, we go from a median AOD of 0.1 to median values greater than 0.2. And as you can see, Southern European countries go from DOD values well below 0.1 to DOD values closer to 0.1 in underperformance days. And so just to stress out the message, these are events that are occurring frequently, and the atmospheric community is actually currently debating what will happen in the future. It seems that these events will not necessarily become more frequent as climate change, but will definitely become more and more intense. So even in those locations that we do not consider desertic, we do not consider arid, we might have to take into account the effect that dust storms can have. So just to give you an idea, here we conducted some analysis to really understand how frequent are these type of events, how frequent are dust storms over some European countries. And as you can see, over the first 4 months of 2024, we registered in between 2 and 6 dust storms events in, in countries such as France, Germany, and Italy. What this caused are capacity factor drop ranging from 40% to 80%. Again, highlighting the need to take into account that these events can have substantial concurrent effects on the photovoltaic capacity. In this chart, I just wanted to show you how the problem can extend beyond the Mediterranean basin and southern countries. Here, indeed, you see how the clear sky GHI can vary during a dust storm, with redder values highlighting the most significant drop in clear sky irradiance. As you can see, in this case, we are talking about end of January of 2024. We had a dust storm actually arriving from the northwest of Europe, interesting therefore northern Spain, even north of Great Britain and Ireland, then moving to England. As you can see how strong was the effect over there, and then moving toward the east, so interesting, Germany, Denmark, south of Sweden, and then the rest of Eastern Europe. So again, these events are massive and can travel for significant amount of kilometers. If you are interested in this type of events, you want to learn more, I need to highlight that the IEA PVPS Task 13 is about to publish a report on extreme weather events that also includes a specific chapter on dust storms. The report is expected to be published in 2025, so please follow up the social media of PVPS if you want to learn when it comes out. It is edited by Lori Burnham and Tanodori Tanahashi. And what we discuss in the dust storm chapter is really how clearly the frequency and the intensity of these events. We also report some case studies for two different locations, but we also discuss how PV plants owners and operators can actually act to mitigate the effect of the dust storms, both starting from site selection, system design, as well as during the dust storm is occurring. So overall, with this talk, I wanted to describe and to stress out how important it is for the photovoltaic community itself to really understand the impact of extreme weather events, because this can have repercussions not just on our technology, but on the electricity grid. And I wanted to show how dust storms fall in that category and which type of impact they can have. Indeed, even in non-desertic countries such as Spain, we registered drop in performance of 50% over 2 weeks period. And these events can also lead, even if the 2022 dust storm was not the case, can lead to some significant soiling losses that will have to be mitigated. I also show how severe underperformance occurs and how often it can occur even for large capacities of photovoltaics. And I highlighted how, in addition to total cloud cover, we can use, for example, aerosol optical depth and dust optical depth to predict the days of underperformance. So thanks everyone again for attending, and thanks to the ICOSES committee for inviting me.